Hello, good afternoon, and welcome everyone to this week's Zoom for Thought Talk, during which Teresa will tell us how to use trees to make life decisions. Take it away, Teresa.
Thanks for the introduction. So here's a quick overview of what we'll be going over. Just some quick motivation, some definitions, overview of the different methods in decision trees, and some applications. So first for motivation, I think this is pretty self-explanatory. Yeah. So some motivation about machine learning. So it is a subfield of artificial intelligence. So AI is basically just any program that can sense, reason, act, and adapt. And machine learning, more specifically, is an algorithm that learns over time when it's exposed to more data. And deep learning is a subset of machine learning, usually involving neural networks, but we're not going to talk about that today. And one of the main considerations in machine learning is the bias-variance trade-off. So bias is defined as the difference between the average prediction of our model and the correct value for which we're trying to predict. And variance is the variability of model prediction for a given data point and the model's ability to generalize on this new data. So for example, if you have a model with high variance, it performs really well on the training data that you use to build the model, but when you try to test it on new data, it'll have a lot of error because it's overfitting. And this is kind of like one of the classical ways of explaining the variance, the bias variance trade-off. So you want to have low variance and low bias. That's this target down here. But when you're underfitting, you're just completely missing what the actual, the underlying data. But then when you're overfitting, you're fitting to each particular data point too much. So you're not actually getting the truth in the center. And this is just more of a graphical way of looking at this. So overfitting, you're kind of like drawing a line to each point instead of drawing like a more general fit. Underfitting, you're looking, it's not even like showing like this parabola shape. So you want a good balance of low bias and low variance. So then you're able to still get the shape of the data with it being able to adjust to new data points. And mathematically, suppose one is trying to predict an output y from your input x, and assume there's a relationship y equals f of x plus some error. Let f hat of x be a model of f of x, then your expected squared error at a point is the expected value of y, which is the output, minus your model squared. And you can expand this further, and then you get that the error is the bias squared plus the variance plus some random error from the model. And this is illustrated in the graph. So as your models become more complex, then you increase the variance. So that's when it's fitting to each individual data point. But then if you have high bias, then you have really high error. So you want to be somewhere in the middle here. And another thing that's important to think about in machine learning is the accuracy explainability trade-off. So a lot of the more complicated models, such as like neural networks, support vector machines, are highly accurate, but they're kind of like black boxes, as in no one really understands the underlying math behind them. But if you have these more simpler models like linear regression or just some like simple classification models, they're really easy to explain and kind of understand how the model works, but they're not as accurate. So decision trees actually fall somewhere in the middle. Like they are pretty easy to explain still, and they have like higher accuracy. And now just some machine learning definitions to prime everyone. So we're going to define machine learning as learning a function f that maps input variables x to output variables y. So basically you map from function space x to y. And an algorithm learns this target mapping function from the training data X. And in machine learning, there's supervised and unsupervised learning. We're going to talk about supervised learning today. So that's when you train your model based on labeled data. So in the data set itself, it has both the input and output pairs. So for example, if you have a data set of different flower attributes, it'll tell you in the data set which type of flower each row is. And in non-supervised learning, just as an example, these labeled data and outputs are not provided. So that'd be kind of like if you're just giving a bunch of attributes about flowers and you're trying to cluster them to see like which ones are each type of flower. But decision trees are supervised learning. So that's what we'll be focusing on today. And a few more definitions. Regression problems is when your response is quantitative. So that's say you're trying to predict like income or things or temperature or those types of things. Classification problems is when your response Y is qualitative. So like there's different classes. So that could be like the different types of flowers. And a non-parametric method is where the algorithm does not make any assumptions about the form of the mapping function. So your model is able to learn from the training data rather than making simplifying assumptions for the function from this like sort of known form as in a parametric method. So this has both advantages and disadvantages. But in the case of decision trees, it allows the model to be more flexible and like adapt to the underlying data itself. So what are decision trees? So taking all those vocab words that you just learned and putting them all together, it's a non-parametric supervised learning method used for both classification and regression. So we'll go over an example in a second. So basically, how decision trees work is they identify how to split a data set based on different conditions. So these decision rules that it splits on are typically a bunch of if then else statements. And the goal in using decision trees is to train a model to predict the value of a target variable by learning these different decision rules inferred from the data features. So based on your data set, it'll generate different if then else statements to like see which ones are most appropriate for the variable you're trying to predict. And some advantages of decision trees is that they're simple and useful for interpretation. So it has that accuracy and explainability trade-off, and also they're computationally efficient. However, they are susceptible to overfitting, and we'll discuss some ways on how we work to resolve that. So one of the main ideas in decision trees is to segment your predictor space X into a number of simpler regions. So for example, in this data set, all of these blue dots are, for example, like counterfeit transactions, and all of these like darker colored dots or points are actual transactions. Like this would be like in a fraud kind of example. So all of these decision boundaries would be kind of like the if else statements. So like they have different characteristics. Like for example, like is it greater than a certain dollar value? That would probably be all these ones up here. And then you have like other factors that they take into consideration to segment this predictor space here. So here's a quick example of like kind of how to visualize a decision tree. So as I mentioned, it's basically a bunch of if statements. So we'll be looking at the survival of passengers on the Titanic. So in this data set, the variables that we have are gender, age, and how many siblings they had. How many siblings and spouses they had is this SIV-SP variable. So just the first split it does is male and female. So just based on gender, they classified them as survived, and they have a certain like percentage of like how many survived. And then for male, they based it on age. So if you were greater than 9, you're likely to die. But if you're younger than 9.5 years old, then it looks at how many siblings and spouses you had. So if you had greater than 3 siblings or spouses, then you're likely to die. But if you had less than 3, then you survived. So I guess that's how you would survive on the Titanic, according to this model.
It sucks for those 9-year-olds with 5 wives.
Yeah, or 5 siblings or whatever. Yeah. And then a regression example. So this is how many hours kids played outside based off of the weather. So this like the outlook is like what the prediction was, and then temperature, humidity, and if it was windy or not. So you can see when it was like nice weather outside, they played for more hours outside. So that table is like your data set S, and then the outlook. So that's the first node that they use to split the data. So in the Titanic example, that would be gender. So we call that the root node. And then you have the 3 options, and this is one branch right here. And then after this branch, then they split each of these based off the algorithm split it based off of the next variable. So in this case, after sunny, it looked at whether it was windy. And if it was true or false, then it was able to predict how many hours the kids were going to play outside. And then it did the same for overcast. And for rainy, it decided that temperature was the next thing they would split on. So then this is the predictor for how many hours they played outside when it was rainy. And so these are all child nodes here. And then this bottom set and this green one here, those are called the leaf nodes or the terminal nodes. And this is going to be like kind of like the flow of how we go through the rest of the presentation. So we're going to start with decision trees and then move through bagging, random forest, boosting, and gradient boosted trees, and XGBoost, which is extreme gradient boosted trees. So we'll start with decision trees. So decision trees is when you have just one tree. So for example, this is Joshua Tree National Park, because there's only one tree in the whole park. So basically how it works is you want to grow a large tree using the splitting criteria. And one of the most common ones is called CART, which is classification and regression tree, which was introduced by Leo Bremen in 1984. And these are some other ones that you can look up or we can talk about after. And then after you grow the tree, you want to prune off some branches to prevent overfitting. And how this works is you basically would like remove like one of the conditions that you use to split one of the nodes. So this would look like collapsing 2 of the internal. So like in the weather example, it would have to be like that middle layer, not the end layer of nodes, using a cost complexity pruning, it's called, which is basically an optimization function to obtain a sequence of the best subtrees, and also using k-fold cross validation, which basically replicates the data set k times and takes the average to make sure that you're getting the best subtree. And we're not going to go over that today, but we will go over the CART method. So CART, in very computer sciencey terms, is a recursive binary splitting strategy to build a tree using a top-down gradient approach. And what that means in English is, at a given node, you consider all variables x and all possible splits s of that variable. Then you choose the best variable to split on, and you split by minimizing the node impurity. And node impurity is kind of a way of measuring the homogeneity of the response classes k at a given node t. So basically it wants to see, are all the things that you split on, when you split it, are they all similar to each other? Because if they're not similar to each other, then you would want to split it using a different method, because that's not a very good way of classifying it. So in some ways that we can measure this node impurity is there's some different metrics. So you let R be the associated region for a given node T, and let P hat K be the proportion of the training observations in R that are from class K. And then we have different impurity metrics. These are just all the different kinds. We'll be using the Gini impurity index and the CART impurity because these are the ones that CART uses, but there's just like a bunch of different ways that you can measure impurity basically. Cool. And then we'll walk through how the CART algorithm works. So you start at your root node T0 right here. And for each J in 1 to P, so those are all the predictor variables in X, you consider predictor Xj. And for each possible split S, so that's like all the different ways that you could create a new node based off of that. You create two nodes, TL, TR, or regions R of L, JS, and R. So basically you're splitting it based off of this split condition S. So this could be like, for example, like the less than 9 or greater than 9 years old split, for example. And then you want to select the best S in terms of overall impurity for the two regions, RL and RR. And you're going to denote these two optimal regions with the star for S. So basically how you can select the overall impurity is you consider the parent node T and two given child nodes, TLS and TRS, which are denoted that way because you're splitting off of the same value S. So you can pretend like this blue one is T and this one could be TLS and this one could be TRS since you're splitting it both at S. And then you want to minimize this function here where Q is the proportion of observations from the nodes and I is the notation for the impurity function that we showed on the earlier slide. So take a second to pause here in case people have questions. Cool. And then the next step is you compare the results of all of the predictors, and then you select the best predictor S and you split. And then you repeat steps 1 and 2 for all of your nodes until the impurity does not improve in any of the terminal nodes. So those are the nodes at the very bottom, or until each terminal node has at least 5 observations, because you don't want your trees to have too many branches. Otherwise, it's very inefficient. So that's for decision trees. So that's when you have one tree. So now we're going to go on to ensemble methods, which is when you use more than one tree. So you have a forest. This is Redwood National Forest, National Park. So one of the great advantages of ensemble methods is you're able to utilize multiple decision trees as weak learners. So basically you underfit all of your individual trees and then you combine them together to have like a strong learner at the end. And this helps reduce the variance. So it helps with that bias variance trade-off we talked about earlier. And this includes basically all the methods that we have left. So bagging and boosting, and then there's some more sophisticated algorithms such as ADA boost, random forest, like GVM, XGBoost, and cat boost. And we'll talk about a couple of these. So first, we'll talk about the difference between bagging and boosting. These are kind of like the most common ones. So first you have a single decision tree iteration. So you're using all of your samples. This is like X1, Y1 to X5, Y5. So the Ys are like the output labels and X are kind of like all the inputs. And you're putting all of the samples into one decision tree. Bagging is when you select a subset of the samples and you train all of them in parallel. So it's a random subset. They could have overlapping. So like you can see like X3 is in multiple samples and X5 is in multiple samples. But you create multiple trees and you train them in parallel. And then you aggregate all of them together at the end. And all of these individual trees that are running in parallel, they will underfit since they're only using a subset of the data. So they're not going to get like the whole picture. Boosting, on the other hand, it does, it takes all of the samples, but it builds multiple decision trees in sequence. So it will weight some of the samples each time and adjust the model slightly each time. So first you weight all of them equally, and then you build a decision tree on top of this decision tree here. And in this case, it weighted X1 and X3, and then you build another decision tree on top of that. So it's kind of like in this one, the model is being passed towards all of these passed along through all these learners. And then in bagging, they're all learning independently. So Random Forest, it was developed by Leo Brenham in 2001, and it's based on the bagging algorithm because they're all developed in parallel. So how it works is you have a random sample from all of the data points, and you also take a random sample of your features available. So like all the different variables that you have. So like in the Titanic example, like the gender, the age, and those sorts of things, you take a subset, a random one each time, and then you train multiple decision trees independent of each other. And then the final prediction is based on a majority vote. So it just takes the average basically. And then AdaBoost was developed by Freund and Shapir in 1996. And it's based on the boosting algorithm. So that's the one where you have multiple trees that are sequentially building on top of each other. And how it works, it combines all those decision trees and it assigns weights to incorrect values. So it's like more likely to be accurate after each iteration. So like builds on top of it. So like this first one, it misclassifies these two blue dots here. So then it weights those ones more. So then the decision boundary moves over here. And then it misclassified this red one here. So then it moves the boundary over here. And then it weights this one. So then it is able to divide the feature space correctly. So it learns from all of the past mistakes here. And XGBoost, known as Extreme Gradient Boosting, was developed by Chen and Gustrin in 2016, and it uses gradient tree boosting. So it's a very, very new method. And it takes the best features from AdaBoost and Random Forest using CART in a sequential learning process. And it minimizes the loss function using gradient descent. So that's where the gradient tree boosting comes in. And it implements parallel processing to increase speed. And it also has regularization parameters to reduce variance and overfitting. Just like going through like a brief overview of how we got from one single decision tree to XGBoost. So decision trees, you're just looking at one tree and it has all the different if statements. Bagging is the first ensemble method where it combines all of them in parallel through and aggregates them through majority voting. And then Random Forest builds on bagging from selecting a random subset of those features for a collection of decision trees. That's why it's called Random Forest. Boosting is where each time you feed the same model through and you build on top of that one. So you're increasing your previous model. So that's where it comes from boosting. And then gradient boosting is where you have the gradient descent built in to minimize your errors in your subsequent models. And then optimized gradient boosting, and it has basically all the features. So it's like the best of everything that came before. So if you think about it, it's kind of like it built a decision tree on top of itself to come up with this last algorithm. Cool. And then we'll talk about some applications. So there's many real world applications of decision trees. So one common one is in business and demand and revenue forecasting. So this is actually one of the projects I worked on during my internship. I was very fortunate to be able to work with a great team of data scientists, and we worked on this XGBoost model for predicting Intel's demand and revenue to help like better understand our customers' needs and also like how Intel would perform. So that was like a really cool experience for me. And also in banking and finance, there's a lot of applications. So one example is the credit card fraud that we saw earlier. And also in healthcare and medicine, there's like so many applications of data science in biotech, especially with gene classification, and they've been using these to like help detect like cancer genes and or diseases and those sorts of things. And in e-commerce, a lot of the different companies are using decision tree models to help change your ads that you receive. So they're using, since it's like a very easy method to explain, they're able to like use that. Yeah, election predictions as well. And in the stock market, people are using decision trees to predict how the stock market goes, and also some sentiment analysis, like if people feel that like it's going to go up or down, I guess. And also in pure math, it could be a potential alternative to neural networks, how they're used in pure math, like learning mathematical structures. So I found this one talk by Yang Hui He, where he's using neural networks to help learn like different mathematical structures, like in algebraic geometry and those sorts of things. So I guess one alternative that like someone might consider using is decision tree based models, since like neural networks are so hard to understand. And then I have my sources here from all the wonderful images that I borrowed from the internet. And yeah, I'll open it up for questions.
First, let us thank the speaker. All right, any questions?
I will just briefly say, I think this is the first for ZFT that has both a math talk and a talk about national parks. So, you know, real congratulations on that.
Thank you.
One for the books. I have a question actually. So you as one of your first examples of an application, you use the fraud detection. I know the algorithms they actually use, like each bank, are probably proprietary or something. But do you have any idea if they're do you know of a bank that uses one of these algorithms in part of its fraud detection plan?
I think not specifically. It's just like always listed in like textbooks that people do use it. Like a lot of the sample data sets that like I learned in undergrad were on like credit card fraud detection. So they like have like the different variables, like how quickly were increments between purchases, and like how expensive the purchases were, and like what types of stores, and also like time of year, like there's more crime certain times of year. So I don't know like of a particular bank, but I do know that they use it in textbooks examples a lot.
Sweet. Very cool. Thank you. Any other questions? All right, let us thank the speaker once more.